Now, we can also define the dot product of two intersecting vectors as the product of the magnitude of those two vectors and the cosine of the angle between them. For two generic vectors, a and b, we can say a dot b is equal to the magnitude of a times the magnitude of b times cosine theta, where theta represents the angle between these two vectors. And we also see this is equal to b dot a. That is, the dot product obeys a commutative property. Now let's consider the dot product for the following vectors: I hat dot j hat, or j hat dot k hat, or k hat dot I hat. We know the magnitude of each of these unit vectors is unity, but the angle between our x and y and z and x axes is 90 degrees, such that the cosine of 90 is equal to 0, and thus the dot product would be equal to 0. That is, we cannot project a vector onto another vector that is perpendicular to it. Now if we take I hat, or j hat, or k hat, we'd have the magnitude of unity times the magnitude of unity times cosine of 0, which is equal to unity. Thus, if we dot a vector with itself, the magnitude is going to be unity. Thus, we note for orthogonal vectors, our dot product is going to be a 0 value, and for concurrent vectors along the same line, i.e. two of the same vectors, our dot product is going to yield unity. Now, based upon our definition of the dot product, we can say for an arbitrary vector f and any unit vector, in this instance we're going to pick I hat, that we can define the angle between them as theta sub x would be equal to cosine inverse of f dot I per the magnitude of f per the magnitude of I. F dot I is just the proportion of f existing in the x direction. The magnitude of f times the magnitude of I is simply the magnitude of f, for the magnitude of I is equal to unity. Thus, we can generalize this equation to calculate the angle between any vector and any principal axis. That is, we can say theta sub x would be equal to the cosine inverse of f sub x, i.e. the x component of our vector, per the magnitude of f. Theta sub y would be equal to the cosine inverse of f sub y per the magnitude of f. And theta z is equal to cosine inverse of f sub z per the magnitude of f. That is, we have three principal angles that define the angle between our vector f and our principal axes. Now, in example 2, let us consider the following force vector, f, which is defined as 5.0, 4.0, 4.0. And we want to determine theta x, the angle between our x-axis and our vector. To do such, we have to determine f sub x, which is taken as 5.0. Next, we must determine the magnitude of f. The magnitude of f is equal to the square root of 5.0 squared plus 4.0 squared plus 4.0 squared. And this is equal to the square root of 57, and expressed to two significant digits is equal to 7.5. Now, we have that the cosine of theta x would be equal to f sub x per the magnitude of f. If we look at the quantity on the right-hand side, we have 5.0 per 7.5. This is equal to 0.66 repeating. And if we express this to two significant digits, this is equal to 0.67. Now we see the output of this trigonometric expression, cosine theta x, has two significant digits, and thus the angle has to be reported with precision in the tens place. For us to increase the precision of this angle, we'd have to increase the number of significant digits, describing both f sub x and the magnitude of f. Therefore, we can say theta x is equal to cosine inverse of f sub x per the magnitude of f, which is equal to cosine inverse of 5.0 per 7.5, which would give us value of 48.19, but if we take into account our significant digits, this rounds to 50 degrees. Say we want to determine theta sub y, the angle between our vector f and our y-axis. To do such, we have to determine f sub y, which is taken as 4.0, and determine the magnitude of f, which remains unchanged. Thus, we can calculate theta sub y as the cosine inverse of f sub y per f, which is equal to cosine inverse of 4.0 per 7.5, which would be 57.77 degrees. But now that we have two significant digits that populates our trigonometric function, we express our angle in the tens place, 60 degrees. Lastly, if we want to determine theta sub z, the angle between our vector f and our z-axis, we'd have to determine f sub z, which is taken as 4.0, and the magnitude of f, which remains unchanged. Therefore, theta sub z is equal to cosine inverse of f sub z per f, which is equal to cosine inverse of 4.0 per 7.5, which, taking into account significant digits, is 60.